Okay, so I will share the screen. So yesterday we talked about all the different multiple BJT networks, and these two very important use cases. One was the current mirror, and another one was a constant current source. So these are the two uses which we covered, and today we begin from here, where we look into PNP transistors once. So in the entire discussion and even in the books, normally you will find the NPN transistors, and in the networks also NPN transistors being used, because they are more like our default sense of positive and negative work very well with the NPN transistors, whereas in the PNP transistors they are just the opposite. That is what we need to only take care of, only keep in our mind. So if we keep that in our mind, we just have shown the same equations, the KVL and KCL, the KVL equations for the PNP here, and as you can see here that your VBE and VCE are defined with the same polarities as we had defined in the NPN transistors also. So as per the defined polarity, we expect that the VBE magnitude will come out to be negative, because we know that actually the actual polarity would be opposite in PNP transistors. The polarity of VBE as well as VC, the actual polarity should be opposite to that in the NPN transistors. So for the purpose of analysis, we have kept the same polarities as the NPN transistors, and when we evaluate these, we will see that we are getting a negative sign, which indicates that in reality the polarities are different. Now here also you see that the currents are in the opposite directions. So these are the important things to note. The currents are in opposite directions. Here we have minus VCC instead of plus VCC, and now if we use the KVL in this loop, in the input loop, so previously we are going in this direction, now we will move in this direction along the direction of the current. So we are facing a drop here, IERE minus IERE, then plus VBE, and then minus IBRB, and then it is minus VCC. So that means there is a plus VCC. From here to ground the voltage is increasing, so plus VCC would be equal to 0. Okay, so first thing to note is that here we have a minus VCC, here we have a minus VCC. So always in the PNP transistors the biasing is done with a negative voltage with respect to ground. The voltage must be negative. Okay, that is one important thing to note here. So now we understood this KVL, and from the KVL we can evaluate what IB would be, and IB takes this form. However, in this form you check that VBE as defined in the circuit is in this direction, but we know that actual VBE is in the opposite direction. So the VBE is 0.7 volt with a minus sign. So VBE is 0.7 volt with a minus sign. So when you evaluate IB, it takes the same form as in NPN. In NPN it was also VCC minus VBE by some resistance, where base resistance and the reflected emitter resistance. So here also it is the same form, VCC, and since VBE is minus 0.7, so something minus something subtracted from the VCC divided by the resistance of the base and the resistance of the emitter reflected to the input side. So that becomes IB, and IB's direction is defined here, and this is as per the PNP transistors usual direction. So So it means that it confirms that this is the direction of the IB, since we have found out IB to be positive. Now let us see the output side. When we do the KVL in the output side, again we start from this point and go towards VCC. What we see is minus IERE, and then there is a plus VCE. So actually VCE should be in the opposite polarity, but according to the diagram we follow plus VCE, then minus ICRC, and then again plus VCC. And from here, if you evaluate VCE, you will find this is taking this form. Sorry, something happened to my whiteboard. Let me again open it up. This is the problem with whiteboard. It opens from the very first instant when one has started writing on it. One has to move up. Yeah. So when you now evaluate the VCE, you will see that this term is dominant over this term. This is very easy to understand because this is the supply voltage and these are the drops in the voltage loop. So obviously the drops cannot be more than the supply voltage. So here this is a dominant term and this is less, this is something which is lesser than this. So ultimately you will see that VC would be negative. VC is less than 0. That means nothing, that only means that the polarities, actual polarities are like this. That is all. Okay. So this is VC. If you had begun with taking VC in this polarity, then of course you would have a minus sign here and VC would have come out to be positive. VC would have come out to be VCC minus IC RC plus RE. So all these are depends on how you have drawn up the circuit, and then you evaluate, you make up your equations as per your conventions that you have used in the circuit, and then according to the value, whether it is positive or negative, it only gives you the idea whether your chosen conventions were correct or they have to be reversed. That's all. So that is about PNP. So if you have a PNP transistor in a circuit, then what you need to do, you please remember that this biasing voltage should be negative. You start with writing this as negative, you make the direction of currents in this manner, and you can maybe you can start with the actual polarities like VC, like here minus and plus, also VB minus and plus here. So in this manner you can start with the analysis. So there would be no confusion regarding positive and negative answers. All answers you will then find are coming out to be positive. Okay. The next application is very important. This is the logic gates. Now what do we mean by logic gates? You may not have any idea right now. Let us look at the circuit and then we will come to that point where we can say something about it. So in this circuit where it is named as OR gate, so what happens in this circuit? Try to understand that first. In this particular circuit, the inputs, there are two inputs, A and B. There are two inputs, A and B, and there is one output C which we are collecting from this point. One output C which we are collecting from this point. Okay. So what we have to only investigate is whether this output is high or low depending on whether the inputs are high or low. Now inputs are high means we are supplying a suppose plus 5 volt. This I mean as high, and low means we are supplying a 0 volt. Okay, so this may not be exactly 5 volts but some higher voltage, and this may not be exactly 0 volt plus but something which is very near to 0 volt. So when we do this, what happens when we have a higher voltage here, then the base is triggered. That means this transistor is now acting as a closed switch. Okay, so this transistor will now act as a closed switch. So the current will flow through this transistor when there is some pulse in the base in this point A. Similarly, when there is a high pulse in the B point, then this transistor will also act as a current, will also conduct the current. Okay, so it will act as a closed switch. Whereas if there is no signal in A or B, then these transistors will act as open switches, because when there is no signal at A, then there will be no base current, and hence there will be no collector current also. So this will be an open switch. So now if we notice this fact, then we can understand very easily from this circuit configuration that if any one of A or B has a high signal, has a high pulse, then this 5 volt will come to this point. Obviously there is a VCE drop, but we can neglect that VCE drop. We can assume it to be very less compared to 5 volt. So what we can say that this 5 volt or a high voltage which is very near to 5 volt will come to this point C. So when any of these A or B is experiencing a high input voltage, then the output is also becoming high, and when both of these will experience a low input voltage, only then there will be no current flowing through these transistors, and hence this potential, the ground potential, will come here. Since there is no current here, in this RE also there is no current flowing, so this potential comes up to this potential, to this point. So C becomes 0. The voltage at C becomes 0 or very close to ground. So if we denote this high as 1 and low as 0, then you now notice this table which is called the truth table. So now you notice this table, whatever we had analyzed is given here. So this one, wherever there is any one of the A and B facing a high voltage which is designated by 1, the output is also coming out to be a high voltage which is designated by 1. Only when both the A and B are facing low voltage designated by 0, the output is also having a low voltage designated by 0. Okay. So this is how the input output of this circuit is behaving. This is just the circuit behavior. Now where from the idea of logic and logic gate is coming in this truth table? In this table, the idea of logic gates, so what is the idea of logic? So the idea of logic is true or false. This is binary logic. I am giving you some introduction for your next semester course on digital electronics. Digital electronics will start with logic gates. So it will be good that you pay some attention to this, because when we are teaching digital electronics, at least I used to teach till the last year. I don't know if I will teach again in the next coming semester. Probably I will not. But I did not used to give much details in the actual analog circuits which make up these logic gates. These are the actual analog circuits which make up the logic gates. So it is assumed that the students know these circuits from their analog electronics course which we are doing right now. So these circuits have to be known to you from this course. Some type of circuits, some type of gate circuits have to be known from this course. In digital electronics, some other circuits will be discussed, of course, but this is an introduction also for that digital electronics course. Now the logic is either true or false. Something can be true or false. Some statement can be true or false. Now if both statements are true, that means in total it is also true. So in that way you can get a sense of how logic works. If one statement is true and another statement is false, then if you combine together, then it can be false. If you do a combination, whereas you say that the statement 1 and the statement 2, if you have an AND, then you ask the question whether this is true, whether this S1 and S2, the statement 1 and statement 2 is true, then you have to verify that both these statements are true. Only then S1 and S2 will be true. Whereas if you ask the question whether S1 or S2 is true, then any one of these being true gives you the answer that yes, S1 or S2 is true. One among S1 or S2 is true. So if you ask this question, true S1 and S2, then this is true only when both S1, S2 is true. This is how logic works. And if you ask the same question here, then any of S1, S2 is true. So one cannot actually, this is very intuitive, this is common sense. One cannot teach this common sense to anyone. This is this we understand from within, and if you are not able to understand it right away, just spend some time over it, you will get it. But the point here is that this sort of logic, this sort of logical operations, so this and or, this and or are called logical operations. This sort of logical operations are now seen to be manifested through electrical circuits. This is an electronic circuit. It doesn't have to do anything with logic. It is just an electrical circuit. Signals, voltage signals, currents are flowing through this circuit. However, if you denote the high level voltages as 1, or maybe you can say true, and low level voltages as 0, which is false. So we normally denote in logic true as 1, false as 0. This is binary logic system. There is only 2 levels of outcome. One is true and another is false. Only 2 levels of outcome. So 1 and 0. Similarly, if you denote the high levels as 1 and low levels as 0, then you can see that this particular output is like an OR operation. That means whether the statement A or statement B is true, any one of these being true will give you the answer yes, A or B is true. So in that manner you see. So here A and B are signals. In actual logical statements, they can be any statement. Here it is a electrical signal. So it has been you can see how the similar concept or the similar principle of logical analysis is also getting reflected in electrical circuits, in some physical hardware. This is very important also to understand that how same principles, so these logical analysis, logical statements are something which is not physical in nature. You cannot show me these statements. You can only have a logical analysis of these statements, whether two statements, whether one statement is true or false, you have an understanding of it. You cannot show me that statement, or why the true, that true doesn't come in the form of some fruit or some duster or some box that you can show me. Truth is truth. We know that it is true. It has happened or it is true, we know for certainty. So this is in the level of understanding. This is in the level of abstract principles, abstract concepts. So how this abstract concept is getting manifested in a physical hardware? Just spend a moment reflecting on this. This is very beautiful actually, and this is how the world actually works. We don't spend time on observing the world in great details, but if you start doing that, you will realize that abstract principles are getting manifested in this physical reality, in this physical world. Whereas as such, the abstract principle you will not be able to show anyone, but they are getting reflected in the behavior of elements in this physical world. And you will notice another thing also, that the same principle gets manifested in a lot of different physical setups. These are principle of logic, principle of logical statements, logical analysis. This is getting reflected in this electronic circuit. However, when you will learn about digital electronics, you will come to know that in the very beginning, this Boolean logic was not implemented through electrical circuits. They were implemented through a mechanical setup, a mechanical design, through mechanical switches. The same principle, but getting manifested through different physical realities. This is how the world works. So behind this physical reality that we observe around us, there are higher principles which are more true. We can say more true. Why we can say more true? Because they are common to many of the realized physical, many of the different physical realities that we observe around us. These higher principles are common to all these physical realizations. That's why those higher principles are more true in nature, So I am just giving this, this is a philosophical take on this subject actually, just giving you this so that some of you may start thinking on this. So this is a very very interesting, and it, like, at least to me personally, it gives me a very it shows me the beauty of how things work in this world, and I gain some insights through that, and I enjoy when like this is an inner enjoyment that I get when I come to realize these different truths, how the world operates. This might be true for some of you also. You might also enjoy looking at the philosophical side of what you are actually studying. So in any case, so first, so we have established that this circuit is nothing, is works in a way which is similar to an OR gate. A gate is just a name given to these operations. So when if some physical setup is manifesting the logical operation of OR, then we call it a gate. We call it an OR gate. Okay, so we call it an OR gate. Similarly, you see here in this circuit is reflecting the behavior of an AND operation, logical AND operation. So how it is doing so? What is logical AND operation? Both the statements must be true in order to for the output to also be true. So if we come to the actual circuit, both these transistors must be on so that the entire system is on. Okay, and when that is on, then only this 5 volt reaches this output C. So when this happens, when both the A and B, when both A and B has a high input signal, only then this 5 volt can reach to C. Only then C also has a high signal here at the output. In all other cases, whenever one of A and B is not high, becomes low, then what happens? One of these switches will be off, will not conduct the current. So the 5 volt, so the current cannot pass through this network, and hence this potential, the ground potential, will reflect at C. So if one of the inputs is 0, then the output is 0. Only when both the inputs is 1, the output becomes 1, and that is shown in this table. This is also called truth table. So this is the OR truth table, this is the AND truth table. Okay. Next one, what we analyze is called, so there are other logical operations also. I will just make this point here. There are other logical operations also which are called NOT. So AND or NOT are the very basic logical operations. NOT means it is simply the opposite of some statement. Okay, some logical statement. So not of a, if you consider in terms of this high or low signals, then not of a high signal is a low signal, not of a low signal is a high signal. Okay. Similarly, there are other operations which are known as exclusive OR. Then there are other operations called NAND, NOR, XNOR. So these are the 5, 6, 7. These are the 7 logical operations that one can perform. These 7 logical operations are what constitutes all the different logical operations that you can think of actually. Okay, and there are different logic gates that can be constructed. Different logic gates that can be constructed using these electronic circuits, but we are not looking into all the different logic gates, at least not at this moment. Okay. So next one is a voltage level indicator. Indicated means simply that it indicates whether there is a sufficient voltage level. So some voltage level we fix in one part of the circuit, and when it maintains that voltage level, there is an indication that it is maintaining that voltage level. That indication normally comes in form of a LED light glowing. So when the LED light is glowing, we can say that yes, the voltage level, required voltage level is there in some part of the circuit. And when the voltage level is not getting maintained, then the LED will turn off. Okay. So how we have arranged this circuit, you see. So we have a 9 volt at this end. So this arrow, this sort of thing, arrow means there can be some other part of the circuit, a bigger network in this side, but that bigger network at this point should deliver 9 volt. So this is what we are trying to convey when we are showing this sort of a symbolism. So in this arrow means there is something, we don't know what it is. Anything can be there, as some other complicated network can be there. What we expect at this point is 9 volts coming out with respect to ground. So whether 9 volt is coming or not, that we have to check now. So that we have to check now. For checking that, we make this circuit from this point onwards. From this point onwards, we construct a circuit in order to check whether the remaining part of the network is delivering 9 volts at this point or not. Okay. So hence this particular circuit becomes independent of any network whose voltage level you wish to check. This is important to understand. This circuit becomes independent of any network whose voltage level you wish to check at a particular point. Whatever point you wish to check the voltage, you just construct a circuit like this starting from that point and connect it to that point. So how this works, let us see. So here you have 2 resistors, and this is like a potentiometer actually. So we set this potentiometer in such a way that we have around 5.4 volts here. Okay, so we can adjust this resistance. Of course, we can adjust this resistance, and then this becomes a voltage divider. Becomes a voltage divider. So there is around 5.4 volts here, and if you look into this circuit, there is a 0.7 volt if it is forward biased. So if there is a current flowing, then it will be forward biased, and there is a 0.7 volt. In that situation, you have, if this is 5.4 volt, you have a 4.7 volt in this direction. Okay. So the first thing is that we should ensure that this Zoner diode is reverse biased. Only then there will be a base current, and that we are ensuring by looking at these potentials. So suppose there is no potential 0.7 volt, even then this 5.4 volt will act as a reverse bias to this Zoner diode, and that will make it start conducting, and when it starts conducting, there is a further drop of 0.7 volt, and hence a total of 4.7 volt is coming in coming at this end. Okay. And now when this happens, so actually Zoner voltage, the Zoner voltage here is 4.7 volt. So we choose a Zoner diode whose Zoner voltage is 4.7 volt. This is what we do actually, because Zoner voltages come with different Zoner potentials. So we choose something which is around 4.7 volt. So I think that this is a standard Zoner diode where the Zoner potential is like this. and then we establish a 5.4 volt at this point by adjusting the potentiometer very close to 5.4 volt. So there must be some voltage which is driving the current, and there is some zonal resistance also. So some current should be driven. So it is very near to 5.4 volt. Now when this is established, what happens? There is a base current, and hence there will be a collector current coming through here, which will give like glow the this green LED. The green LED will start glowing because of the collector current. Now for some reason, if this 9 volt drops to some value, suppose 8 volt, it becomes 8 volt, then what will happen? This 5.4 volt will no longer be 5.4 volt. It will also drop. But as soon as it drops, then the condition in this circuit will not give rise to a reverse bias in this zonar voltage, in this zonar diode. So this will stop the current in this output green LED. So the LED will stop glowing. This is what will happen. So a drop in this voltage level will cause the current through the green LED to become 0. Okay. This is how it is working. Then there are other circuits, the constant load current. We already saw how we can make a constant current source, and here we have connected a load in that, and we know that how we can create the constant current source, because by making the IB level constant, we can create one. Another is that we can make it independent of IB, and this is a the voltage divider connection, where we are making the IC independent of IB, and hence we are getting this current IC becoming very constant, and it almost behaves in this manner that we can suppose that there is a current source IC which is driving the load. And this is another circuit where we simply have we don't use this this is more stable actually. This one is more stable. This has reduced sensitivity to changes in beta, but here in this one we have this IC current established through the IB current, and what happens when there is a change in load? Actually, in this case, IC does not change. IC does not change, but the load changes. So the load line, this load line gets changed. Actually, this IC level remains same. This IC level remains same, but the VCC by this load, VCC by R load, this point keeps on changing along this axis. VCC point remains same, VCC by R load point changes, hence we get different load lines. So the load line intersection with this IC output characteristic curve is at different points, but on the same curve. So the Q point actually changes, the Q point changes, but the load current remains same. The last one, another application, very well used or very well known application is for relay driver. So what does a relay do? A relay is a switch which closes or opens based on some input signal, based on some input which comes to that relay, and that input, this input is due to some fault. Basically, relays are basically used in order to cut off parts of the circuit which are not operating in a correct way. So there is some fault in some part of the network or the circuit, that fault gives rise to some signal. This signal is fed to the input of the relay, and then the relay trips. We say the relay trips. So the relay tripping means it cuts off that part of the circuit. And whenever the circuit again becomes healthy, that means the fault condition is no longer there, what will happen? The signal which was generated due to the fault will also no longer be there. And in that case, this signal which is coming to the input of the relay driver, that signal will no longer be there, and the relay will again reconnect. So it had opened the circuit, now it will reconnect the circuit. So this sort of a automated connection and connecting and reconnecting or disconnecting and reconnecting operation is available with the relay. And this works mostly in the principle of magnetism. So there is a solenoid which charges up, due to which it attracts the switch and makes it closed or open, and when the solenoid discharges, the attraction to that particular mechanical switch is lost and it is either closed or open, the opposite one. Okay. Now how it works, it is very simple. This trigger input voltage, which is the voltage coming due to the fault occurring and some part of the circuit, this is the trigger signal. Trigger signal applied at the base gives rise to a collector current which charges up the solenoid. This collector current charges up the solenoid, and hence it cuts off the relay. The relay operates, and the circuit which the relay is connected with, that is taken out of the entire network. So that part is cut off. Now when the relay signal, this trigger signal becomes 0, then what would happen? This current will become 0, and again the circuit will be closed. Okay. But now there is a problem. What is the problem? The problem is that this current does not become 0 all of a sudden, because we know that the current through a solenoid cannot change instantaneously. This current cannot change instantaneously. So there will be some high voltage spike, and the more it tries to reduce, the faster it tries to reduce, the greater amount of voltage will be produced across the solenoid. This we know from basic understanding of our inductors, how the inductors work. And when this voltage is, if you see that this VCE voltage is VCC minus this VL. So when this VL is having a large spike, this VCE will also be very high. But VCE becoming very high leads the transistor to the breakdown region. Remember the collector curve, VCE being very high leads the transistor to the breakdown region. So the transistor can get destroyed. The transistor can get destroyed. In order to prevent this, we have to include a diode with this relay. So what does the diode help you with? This diode takes in the current. So when this has to go off, then the relay voltage is in this direction, and the current is driven through the diode, not through the transistor. So the transistor gets saved in that manner, in that way. And in some time this current becomes this spike gets reduced, and there is this internal resistance also of the diode. So all this coming in together makes the current go down to 0 in some time. So in this way the relay driver is operated. So the important thing is to put the diode in this network, so that to save the transistor. So this is all that I had in DC analysis of BJT. So from next day I will go to AC analysis, and I will not continue further today. So if there is anything you wish to ask, you can ask me. Go through the book, you will find a lot other examples also, lot more examples also on various applications of BJT. And as you can see that all these applications did not have anything to do with an AC signal coming to the input. So these are purely based on the DC biasing conditions. All these applications are purely based on the DC signals which can act on the BJT. The input in the base side also we are supplying DC signals. Okay. So from next day onwards we will see what happens when we apply AC signal to the base. Okay, so with this I think we can stop now. So thank you for being here, and if there is any doubt, any question, please write to me, and I will try to explain them in a better way. Okay, thank you.
Thank you, sir.